last class we were seeing about the problems, right? Now, so we'll continue with the thing. So the process we have seen like isobaric, isoporic, adiabatic, everything, right? Now let's look into the topic the cyclic. What is cyclic process, non-cyclic process, and quasi-static process? So in last class we were discussing about the isobaric, isoporic, adiabatic, right? Now, so isothermal. These are the processes we have seen, and let's go. The next topic is cyclic process, a non-cyclic process, quasi-static or equilibrium process. Okay, so let's decode and understand it's simple. So cyclic process is nothing but when we talk about a system, okay, a system undergoes a change but it returns to its initial position. For example, if I take point A, so point A is going to point B, again point C, again point D, again it is going to point A. Okay, so when I am starting with point A, going to B, C, D, and again to A, which means I am going to the same initial position. So final state is equals to initial state. That is the cyclic process we say. And for example, if we take the example, best example is 8 engines. Okay, then what is non-cyclic process? A system does not return to its original state. Okay, for example, if I take like this, point A, B, C. So it has point A to B, B to C, that's it. Okay, so example, eating a water from 20 degree to 60 degree Celsius, right? So this is about the difference between the major difference between the cyclic process as well as the non-cyclic process. When we talk about a quasi-static process or equilibrium process, okay, quasi-static or equilibrium. So quasi, we have learned the meaning of quasi, it's nothing but slow. So quasi-static process, it's a slow process we learned in the previous classes. So happens very slowly, so the system stays close to the equilibrium all time. It's very slow, like it will always stays near to the equilibrium condition. That's the thing they are saying. And pressure and temperature are uniform throughout. What's the thing? It is important, guys. So pressure and temperature, which is constant in quasi-static process. So pressure is constant, temperature is constant. So used for theoretical calculations. Okay, so this is the cyclic process, non-cyclic process, and quasi-static process meanings. Okay, and once you have taken down, we can go for the next thing. Okay, so the next one is, yeah, so we will start with the cyclic process, for example. Okay, and if we see here, I am going from A, B, C and D again to A. Right now, that's the thing we have discussed in the previous slide. So what is constant here? Like process returns to the initial state, so internal energy will be 0. Internal energy will be 0. And what about internal energy 0 means what about the thing which we have learned in the first law of thermodynamics? Q will be equals to W if U becomes 0. If U becomes 0, Q will be equals to W. That's it now. We know that delta Q is equals to delta W plus delta U. So if we neglect it out, which is 0, then we will consider only delta Q is equals to delta W. Like whatever the heat is there, it is equals to the work done. And if we find the work done, we have got the heat value. Okay, that's the thing we have learned in the cyclic process. Got? So next one is heat engine. Heat engine. So heat engine is a system that converts heat into a work. So what is the thing here? We are taking heat, like hot reservoir is there. Okay. So we are taking to the working substance. Okay, working substance. So it will do some work and give out the output, and the remaining will be to the cold reservoir. So it consists of a working substance. Example, a mixture of fuel vapor and air in a diesel engine. Okay, diesel engine. So hot reservoirs, it's always in high temperature. Like hot reservoir, it's always in high temperature. And when we talk about a cold reservoir, it is low temperature. Low temperature. Right? So it's a working substance which consists of fuel vapor and air, which is in a diesel engine. Right? So this is the thing. So working substance is there, and hot reservoir and cold reservoir. So the heat engine takes Q1 heat, like Q1 heat from hot reservoir at temperature T1, releases Q2 heat to the cold reservoir at temperature T2. So by doing this, it delivers the work to the surrounding. So when we talk about in terms of formula, so W will be equals to Q1 minus Q2. Okay, Q1 minus Q2. For how much? For one complete cycle we are talking. For one complete cycle we are talking, W is equals to Q1 minus Q2. Right now? So what about the efficiency? Efficiency is nothing but the amount of how much amount of work it has been done. Like it is the ratio of work done by the system to the heat absorbed. Like we are observing something. No, we are observing something. If I give the total amount, okay, if I give the total amount, for example, we are reading for exam. Okay, we are reading for exam, and we are securing the mark as 35 out of 100. So what is my efficiency? So 35% is my efficiency. Right now, suppose if I get 77 out of 100, so my efficiency is 77%. If I get 99 by 100, my efficiency is 99%. So if I get exactly 100 out of 100, my efficiency is 100%. 100%. That's the thing. Right now you got like we have taken the exam for 100, but we are delivering it for only 35 marks, which means my efficiency is 35. Right now, if we deliver whatever the amount we have taken, then the efficiency will be 100%. But yes, we'll look over here. So it's the ratio of work done by the system to the heat absorbed by the system. Okay, so which is nothing but eta is equals to W by Q1. So the work done only we are giving. From where we are taking? From Q1 we are taking. Okay, I am producing the work done from where? From Q1. So W by Q1. So what is W? We know that W is nothing but Q1 by Q2. So when I take eta is equals to Q1 by Q2 by Q1. So if I take this one, no, Q1 by Q1 minus Q2 by Q1, no. So this 2 will get cancelled. So 1 minus Q2 by Q1. That's the eta value we have got here. So I can write in terms of temperature also. No, this is in terms of heat. So temperature T2 by T1. T2 by T1. So for Q2 is equals to 0, then efficiency is 1. Which means we are taking Q1 and Q2, and this is my working substance. Okay, working substance. So some amount I am producing here. For example, 5. I am producing here how much? 4 we will take 4. Okay, work done we have given is 4, but the input we have taken is 5. So how much will be remaining here? It will be 1. Right now. So what is the efficiency? Efficiency is nothing but the work done by Q1, which is nothing but 4 by 5. So 4 by 5 in a sense, how much? So it is 0.8 na? 0.8. So it is 80%. percentage. So for heat engine will have 100% efficiency is never possible. It's never possible. Okay. In converting heat into work, it's never possible. Okay. So this is about the efficiency. This is about the efficiency. You can take a note of this and we can move to the next slide. Done? Can we go for the next one? So now refrigerator. Heat engine is completed. What about the refrigerator? What is the meaning of refrigerator? Okay. We will look into the topic and we will go through the examples. Okay. Refrigerator, AC thing. So what like usually those material do? It gives the cool temperature, like a low temperature it will give, right? No. So what is the thing we will understand over here is refrigerator. Refrigerator is a reverse of the heat engine. Heat engine, okay, reverse of heat engine, which means we have learned about the diagram part of heat engine here. No diagram part of heat engine. So like exactly it will be reverse. Like Q1 will be in this direction, again Q2 will be in this direction. Right now, we will see here. Okay. So work done. Q1 and the Q2. Okay, so the hot reservoir, cold reservoir, and this work done. So exactly opposite. Right now, exactly opposite. The heat engine takes Q2 from cold reservoir at the temperature T2. Some external work is done on it, and heat Q1 is released to the hot reservoir at temperature T1. Got it? So by energy conservation, no. So when I talk about the working substance, W and Q2 will be equals to Q1, right? So therefore W will be equals to Q1 minus Q2. Okay, Q1 minus Q2. Right? You can take a note of this. Right now? So Q1 minus Q2. Here also same thing, guys. If you notice here, Q1 and W, right? No, Q1 and W. Let me take here. So Q1 will be equals to W plus Q2. W plus Q2. Got it now? So I am taking something and giving 2. So which means Q1 will be equals to W plus Q2. W will be equals to Q1 minus Q2, right? That's it now. So in that case, W is here, Q2 will be here, Q1 will be here. I am taking two things and giving one thing, which means W plus Q2 will be equals to Q1, where W is equals to Q1 minus Q2. We are getting the same thing. Got it? So this is the thing we have done there also. Okay, that's the thing we have done here. Right? So when we talk about the efficiency in the heat engine, similar only, but the term is different. The coefficient of performance we will say COP, coefficient of performance of the refrigerator. Okay, which is denoted by the alpha. We denoted by the symbol alpha. Okay, so what is alpha? Like the heat cold, like T2 we have taken, and we have taken with respect to W. So alpha will be equals to Q2 by W. So what is W? Where Q1 by W by Q1 we have taken na? Here in the reverse process Q2 by W. So what is W? So Q2 divided by Q1 minus Q2. Right? No? Q1 minus Q2. So in terms of temperature T2 by T1 minus T2. This is alpha. That's alpha. Right now? So alpha will be equals to Q2 by T1 minus Q2, or alpha will be equals to T2 by T1 minus T2. Right now? You can take a note of this. Done? Okay. Now the next one is second law of thermodynamics. Okay. So in second law we are going to see the two things. So one is Kelvin Planck statement. Second one is Celsius statement. So Kelvin Planck statement, what is saying? Kelvin and Planck. Okay. So no process is possible whose sole result is the absorption of heat from the reservoir and a complete conservation of heat into work. Okay. It's saying like no process is a sole result, which means it's absorption of heat from a reservoir and complete conservation of heat into work. We have taken the hot reservoir and given the heat to the working substance, and if the remaining heat is there, it has been given to the cold reservoir. Right? No. So he is saying that no process is possible whose sole result, like all result has been given into the efficiency, like proper efficiency, 100% efficiency. It's not possible, he is saying. That's the thing. Like complete conservation of heat into work, it's not possible. And what is the second person is saying? No process is possible whose sole result is transfer of heat from a colder object to a hotter object. So we'll see once again. No process is possible whose sole result is the transfer of heat from colder object to the hotter object. Got it? So it gives a fundamental limitations, okay, to the efficiency of heat engine. Okay, efficiency of heat engine, that is eta, and coefficient of performance alpha. So whatever the things which we have been seen in the last two slides, na, like efficiency eta, which is nothing but W. Eta is equals to W by Q1, whereas alpha is equals to Q2 by W. Right? So these two formulas only they are talking over here. Okay? I guess so. The audio is clear now, no? Yes. Done? Okay. So next one is a Carnot engine. So a reversible heat engine operating between two temperatures. Okay. So Carnot engine consists of a cylinder with a frictionless piston, then hot reservoir, cold reservoir and insulating stand. Okay. So the working substance of a Carnot engine to be a ideal gas. It will be a ideal gas. Okay. So like the hot reservoir will be there, insulation stand will be there and cold reservoir also will be there. So we will talk about the process. What are the process? 4 processes are there. Okay. 4 processes are there. When we talk about the 4 processes, no, one is isothermal expansion, isothermal compression will be there. Then adiabatic expansion, then adiabatic compression will be there. Okay, isothermal expansion, then isothermal compression, then adiabatic expansion, then adiabatic compression. So what is the difference between this isothermal and adiabatic? How to find that graph? We have learned that, no, when we talk about the graph, like adiabatic graph will be more steeper than the isothermal graph, no. So when we talk about this is 1 and this is 2, so 1 will be my isothermal, and second one will be my adiabatic. Okay, adiabatic. So 4 processes are there. Let me explain each process one by one. Each process one by one. So first one. So when we talk about step 1, no, we are placing a cylinder on the hot reservoir and the heat is absorbed by the gas Q1 from the hot reservoir at temperature T1. So isothermal expansion, the gas takes place, like the work done will be there, no. So what is the work done here? So it is Q1. Like when we talk about the cyclic process, the internal energy will be 0. So work done will be mu RT, like nRT. PV is equals to nRT, right? nRT. So work done, we know that work done is nothing but P into V2 minus V1. P into V2 minus V1. So from work done 1 to 2, nRT ln V2 by V1. Okay. So we need to remember this work done. At final now we will calculate total work done will be equals to W12 plus W23 plus W34 plus W41. Okay, the total work done we will add up, like sum up. Okay. So next one we will see work done. Okay. So NR into T1 minus T2, like the temperature from T1 to T2 it's going na, right? I mean no, T2 to T1 we are going na. So we are going from T2 to T1, here T1 to T2, like it's expanding and it's compression, right la? So when we talk about NR into T1 minus T2 by gamma minus 1. Okay. So next one. So here nRT 2 ln V3 by V4. In that case nRT1 ln V1 by, so V2 by V1, right now V2 by V1. So next one, final one, nR T1 minus T2 by gamma minus 1. Okay, now we will find the total work done, the total work done. So W is equals to W12, 23, 34 and 41. Okay. So finally we will get W is equals to nRT1 ln V2 by V1 minus nRT2 ln V2 by, so V3 by V4. And what about the efficiency? Efficiency is nothing but 1 minus T2 by T1. You can take only the formulas. So formula is important for us, right now. You can take the formulas like derivation, you can leave it. You can neglect the derivations, okay. You can take out the formulas. Done. Okay. So next one we will see what is the Carnot theorem. Okay. So two given temperature like T1 and T2. What is T1 and T2? T1 is a hot reservoir and T2 is a cold reservoir. So no engine can have efficiency more than that of Carnot engine. Okay. So we have seen a heat engine, we have seen a refrigerator. So no one can have efficiency which is more than the Carnot engine. That's the thing. Second one, the efficiency of a Carnot engine is independent of nature of the working substance. Okay, it is independent of nature of the working substance. Okay, right. So there is the 2 points. Next one, yeah. So the last point, if we see, no, like we have learned about, like this is not like a normal example thing we have taken, leave about the example thing. Okay, so no engine can, like no engines can have efficiency greater than the Carnot, right now. So which shows that Q1 by Q2 will be equals to T1 by T2. It's a universal relation independent of the nature of the system. Okay, so this is about the thermodynamics chapter, and with this I will conclude this chapters. Okay, so in next class we are going to concentrate on the EAPCET questions, okay, of this chapter, right. So be attentive to the classes on time. Fine. So thank you guys. With this I will conclude this today's session of the EAPCET thermodynamics class. Thank you.